kyanite migmatites in eastern Bhutan in the Himalayas, really focusing on trying to understand a fundamental question when it comes to collisional origins, and that's what drives the change between burial and exhumation. So in collisional origins like the Himalayas, we have continental collision, we bury the rocks deeply, and then how do we get them up to the surface? There's a number of different tectonic models that have been put forward to describe this. And in the classic channel flow model, when we bury our rocks, we get them to temperatures and pressures where we can melt them. And once we've melted them, then we've created the low viscosity channel for our metamorphic core of our mountain range. That's the blue unit here, the Greater Himalayan sequence. And this low viscosity channel can then be driven up towards the surface. And that's what happens. That's how we change from burial to exhumation. This is a bit of an end member model, but it's a useful framework in which for us to place our work. And since then, a number of kind of hybridized models have been put forward as well, including this one by Corrosi, which is kind of describing an under-thrusting model. So instead of the whole of the GHS moving as one coherent unit, a number of thrust sheets can develop throughout it, and it means that the base of the GHS is the last thing to come up to the surface. So in our channel flow model, we'd be expecting melt to be forming at around 35 million years, whereas in this model, we can expect it to form at a couple at various different times, depending on where it is in that structure. Where it is in the GHS. Why was I looking at kyanite migmatites? Well, the large granites that we see in the Himalayas, the large granite plutons and the North Himalayan granites and the High Himalayan granites, they contain sillimanite, and they're formed due to decompression melting, muscovite dehydration melting during the exhumation path. So they're not the ones that are responsible for this change. And various people have found that we can have a Oligocene age melting, so 30 million year old melts that form in the kyanite field. And maybe that's partially due to the presence of water as well, that we can have kyanite migmatites forming at kind of lower temperatures and forming kyanite as our aluminosilicate in that melt forming reaction. So this is just a quick flash up of the geological architecture of the Himalayas and where the evidence for all this different type of melting is found. And in red here is where we've got evidence of a Oligocene melting, either with or without kyanite. And we decided to go and have a look at kyanite migmatites that were in the eastern Himalayas out in Bhutan here. This is a geological map of Bhutan, and everywhere that I found the kyanite migmatites, they tended to be at the base of this Greater Himalayan sequence. So the very deepest bit of our GHS sequence down towards the MCT. There was one kind of outlier up here, but most of them were in and around this area here. We have a look at what they actually look like in the field. So the kyanite migmatites, you've got this these discontinuous lenses of kyanite leucozome that contain a little bit of muscovite, kyanite, and then quartz and feldspar, and they're found within these kyanite biotite schists. Again, a little bit of muscovite still left in there, but they need to be quite mica-rich in order for you to find these kyanite leucogranites. Sometimes there's some garnet in the schist, sometimes there's some tourmaline as well. And what we think happened is that due to muscovite dehydration melting of this schist, we were able to produce this kyanite leucogranite. And that melt has not migrated further than you see at an outcrop scale. So we see no evidence of it moving, that migrating upwards and kind of pooling elsewhere. We think these are pretty much in situ, in source migmatites. They're found within the rock that they're sourced from. So when I got my rocks back, I was interested in trying to find out how the kyanite formed. And I was able to figure out that I had 5 different types of kyanite in my kyanite migmatites based on their morphology and their microstructural position within the rocks that I was looking at. And so I've got them all here. So kyanite A are kind of these chunky, typical bladed kyanites that are found in the schist. Then we've also got very similar bladed looking kyanites that are found in the granite, in the leucozone portion. Then also in the granite, we have these rounded, more corroded-looking kyanites that are surrounded by optically continuous grains of muscovite. Again, in the granite, we also have kyanite D, which are much thinner, kind of skinnier kyanite grains. They're not found everywhere. And then we've also got kyanite E, which is also found in the granite, but mainly in one sample in particular. They tend to be larger grains that have lots of quartz and rutile inclusions. Some of them can be quite big. So we identified these 5 different types of kyanite, and then to investigate them further and try and find out how they formed, I did some cathodoluminescence imaging to look at their internal textures, and most of them came back quite complex, and it can be quite often to delineate the differences between them. But what I want you to take away from this is that kyanite A, kyanite B, and kyanite C, they all have quite complex internal zonation. Sometimes you can see some sector zoning in there and some interesting features, but they can generally be described as complex. If we compare them to kyanite D, those skinny blades that we find in the granite, kyanite D doesn't tend to show internal zonation, so it can have a little bit of variation, and it's quite hard to see in this image here because the feldspar is quite bright, but very little internal zonation, so maybe kyanite D formed in a different way. We then compare it to kyanite E, which has an even more complex internal zonation, and you can really see the kind of quartz and rutile inclusions that are in this one. And these can often be really big grains as well, where you can convince yourself that there are subgrain boundaries and maybe they're an aggregate of grains altogether. So some kind of interesting similarities and differences between our CL textures. I wanted to figure out what was causing these CL textures, because they're clearly recording changes as the grain is growing. And we also, we have evidence where you can see that you've got growth zonation on the outsides of some of these grains. So sometimes it goes from bright to dark, sometimes it goes from dark to bright, but you can often delineate these 2 different zonations in kyanite B and kyanite C grains, which are the ones that are found in the melt, so we think that that's reflecting changing melt conditions. So trying to figure out what the CL represents, so it represents the underlying chemistry of the kyanite. We did some laser ablation ICP-MS maps. We only mapped for chromium, vanadium, and germanium. And when I produced chromium vanadium maps, these matched up really well to the CL internal textures that we were seeing. So where we had features where we had high chromium vanadium, that was where the CL was brighter, and where the CL was darker, that's where we had the lower chromium vanadium ratios. So chromium vanadium ratios are changing as the kyanite is growing, and the kyanite's able to record that, which was pretty interesting. And kind of going back to how all these different things, the different kyanites formed, kind of linking that with some of we did some laser ablation spot analyses as well, which I don't have time to show you the full details of, but we saw various chemical changes between these different kyanite populations. And the way that we think these different kyanite grains formed is that we basically had a kyanite that grew subsolidus in our schist, then melt was produced, and some of that kyanite became entrained into the melt. That's our kyanite B. So our kyanite B is effectively a xenocryst in that melt. It didn't form there, but it's ended up there. You might get some continued growth in that. But then you also see a reaction between that kyanite B grain and the melt, and the kyanite B begins to dissolve. It gets that rounded shape, becomes a kyanite C. And then you also have a back reaction between the kyanite and the melt to form that muscovite around the outside of it. Also, when we have melt present, we have the growth of those thinner, skinnier kyanite D grains. And interestingly, they show an increase in germanium, as does the growth around the kyanite C. They both are enriched in germanium versus all the other different types of minerals that we see. So that's kind of telling us that germanium is being released by the kyanite that's dissolving, and then it's going back into kyanite and other muscovite that forms. If we look at our kyanite E grains, those ones in the melt with the quartz and the rutile inclusions, we think that that's evidence that it was peritectic growth. So when we went through our muscovite dehydration reaction, we formed a peritectic aluminosilicate, and then we were also able to see continued growth kind of epitaxially around the outside of that kyanite E grain to form extra zonation. I was able to do some geochron on some very small zircons that were in some of my samples in thick section, and we think they formed they kind of peaked at 22 and about 14 million years ago, which is inconsistent with our classic channel flow model, but works with that corrosive underthrusting model where the bottom of the GHS is the very last thing to form, is the very last thing to be exhumed. So these melts could still work in that kind of that melt-driven exhumation model. And I think I'm a little bit over time, so I will just leave you with my conclusions and look forward to answering some questions.
Thank you very much, Stacey. That was really great. There is a question about, did you analyze titanium in your kyanites in addition to the chromium-vanadium ratios?
We did, and so titanium is a known CL activator, so we were expecting titanium to be varying across our grains. When we did our preliminary work, we didn't see any kind of systematic changes in our spot analyses with the titanium. So that's why we didn't do it for mapping. And yeah, we occasionally see some variations, but I couldn't really figure out anything that conclusive about the titanium concentrations in the kyanite. It's in there and it varies, but I couldn't figure out why.
Great. Somewhat of a follow-up, Rich Palin asks, why did you target the elements you did?
Yeah, so I guess for the mapping, you can do more elements. It's just a kind of analytical decision, and we decided to just do those three. We did some preliminary spots, and in areas where I knew that the CL was bright and where it was dark, and they seemed to match up really well to higher chromium content, vanadium content, and then we managed to hit on this change in germanium content, which germanium's never been measured in kyanite before. Nobody's reported germanium contents in it. The maximum that you get is kind of tens of ppm, but we thought that was interesting, so we thought we'd map it. But yeah, I would be really interested to do some titanium maps of them as well, and because that's what we assume is controlling the CL, but I don't think it is. I think it's the chromium. Okay,
we have time for another question. Catherine asks, how important do you think is the dissolution precipitation of the mechanism you described?
How important for what?
I don't know, Catherine. Catherine, do you want to say something to your question?
Sorry, I was trying to type really quickly.
Yeah.
I guess just for controlling those reactions in the kyanite, I was wondering whether getting kind of coupled dissolution, precipitation, and how important fluids are, as well as the melts.
Yeah, so I think fluids are super important for what's allowing. I think it's a fluid present muscovite melting that's happening a lot of the time. Whether or not that's bringing in elements from different sources, I'm not entirely sure. But I think that's fluids responsible for the kind of continual but kind of punctuated formation of melt. With the coupled dissolution precipitation, yeah, there aren't a lot of trace elements that you find in kyanite, so there weren't that many things that I could then match up to the muscovite, but it only seemed to work in this germanium, and it was interesting kind of the length scale at which this happens, because it makes sense if a kyanite is releasing germanium and then it's just going into the muscovite that's forming around it. But the fact that we see the germanium enrichment in a different type of kyanite that's often centimeters away from that dissolving kyanite was kind of interesting. So it kind of, yeah, it was a surprising amount of mobility. I'm not entirely sure what we know about germanium as a trace element and how far it should be able to go anywhere. But it was, yeah, it was interesting that they were the length scales that we were talking about. Does that answer your question?
Yeah.
Cool, thanks. I saw someone was looking for melt inclusions in the kyanite with quartz inclusions. We don't see any melt inclusion. I do see melt films around the outside, kind of in between that kyanite and that inclusion. So yeah, that suggests that it's definitely melt present. Yeah.